In this lesson, we're going to look at the graphs of exponential functions and logarithmic functions. One of the things you're going to learn is that the inverse of an exponential function is a logarithmic function. So let's for example, let's go ahead and graph the following exponential functions. Let's go ahead and graph f of x equals 2 to the x. All right, so we're going to go ahead and graph this exponential function, and you all know how to graph this particular exponential function. So remember, the horizontal asymptote is, in this case, y equals 0, right? Because you can write this as plus 0 here. In other words, you can say f of x equals 2 to the x plus 0, and this is your horizontal asymptote. And we're going to go ahead and plot, so let me write this down, horizontal asymptote is y equals 0, or the x-axis. Now we're going to go ahead and plot a couple points, or a few points rather. And so if x is 0, we know that 2 to the 0 is 1. If x is 1, we know 2 to the first is 2. If x is 2, we know 2 squared is 4, right? All of this, all we do is just substituting into x here. If x is 3, we get 2 cubed, which is 8, and so on, right? Now let's do some negative numbers, because we know that the domain of an exponential is going to be all real numbers. So from negative infinity to infinity. So let's go ahead and use some negative numbers as well. So if x is negative 1, we get 2 to the negative 1, which we know to make that exponent positive, we have to rewrite it as 1 over 2. So that's 1/2. If x is negative 2, we get 2 to the negative second power. And we know to write this exponent as positive, we have to write this as 1 over 2 squared, which is 1 over 4, and so on. All right? And so what we get is this. So let's go ahead and graph this. So I have the horizontal asymptote here for this exponential function. And I have 0, 1. I have 1, 2. I have 2, 4. I have 3, 8, right? And on this side of the y-axis, I have negative 1, 1/2, and then negative 2, 1/4. Now remember, this exponential function gets closer and closer to the horizontal asymptote without touching it or crossing it. And on this side, as we go from left to right, the graph, or the y values, increase rapidly, right? Okay. Now what I want to do now is remind you that I can graph the inverse of this exponential function. So remember, this is f of x equals 2 to the x. So to graph the inverse of this exponential function, and notice it is 1 to 1, right? So this exponential function, all these exponential functions, regardless of which one you're looking at, in this case I'm looking at the one that has base 2, but all these exponential functions are 1 to 1, so they have to have an inverse, correct? So to graph the inverse, let's remind ourselves that we're gonna remind ourselves that the two functions that are inverses of each other are symmetrical about the line y equals x. So let's go ahead and graph the line y equals x. So y equals x, 0, 0, 1, 1, 2, 2, 3, 3, and so on. Negative 1, negative 1, negative 2, negative 2. So remember, y always equals x. So that's why we're saying 1, 1, 2, 2, 3, 3, and so on. And so when I graph this line, I'm going to go ahead and graph it as a dotted line. And so we get something that looks like this. So there's the line y equals x. And remember, y equals x divides the first quadrant and the third quadrant into two equal parts. So all these are 45-degree angles right here. All right, now remember, when graphing the inverse, all you're doing is interchanging the coordinates, right? So see this point right here, which is 0, 1, right here, 0, 1. It becomes the point 1, 0 on its inverse, doesn't it? 1, 0 right here. The point here, which is 1, 2, right here, 1, 2. I'm going to go ahead and write it here, 1, 2. On the inverse, it becomes 2, 1, which is here, okay? The point here, which is 2, 4, 2, 4, becomes the point 4, 2, which is right here. This point here, which is 3, 8, becomes the point 8, 3, which is right here. This point here, which is negative 1, 1/2, negative 1, 1/2, becomes 1/2, negative 1. So that's right here. And you see this horizontal asymptote here? So this horizontal asymptote, remember the exponential gets closer and closer and closer to the horizontal asymptote. So when I look at the graph of the inverse here, so the graph of the inverse, it gets closer and closer to the y-axis, right? Which is going to be the vertical asymptote. All right, so it's going to be the vertical asymptote. So notice that an exponential function has a horizontal asymptote. The inverse of an exponential has a vertical asymptote. All right, now this is this is an exponential function. We call this function the inverse of the exponential, but it has another name to it. This is going to be called the log function. So the inverse of an exponential is a log function. All right, so the inverse of an exponential is a log function. And since the base is 2 here, then the inverse is going to be g of x. I call this f of x. I'll call this g of x. G of x, which is log, L-O-G, base. Remember when you wrote bases in previous lesson for logarithms, you have to have a base. If there's no base here, it's understood to be a 10. Remember that? A 10. But my base here is 2, so they have to match up. And then my variable is x. All right, so the exponential function is 2 to the x. The log function is log base 2 of x. Log base 2 of x. All right, so notice that the graph of an exponential and its inverse, which is a logarithm, are symmetrical about the line y equals x. All right, so also remember that an exponential function has a horizontal asymptote. A log function has a vertical asymptote. All right, a vertical asymptote. All right, a couple of things I want to remind you about these two functions. So let's talk about y equals 2 to the x. So f of x equals 2 to the x. All right, so we know that the horizontal asymptote is y equals 0, right? Y equals 0, the x-axis. We know that the domain of an exponential, remember this part here, the domain of an exponential, remember, is all real numbers, right? So it's all real numbers. As you go from left to right along the x-axis, each x value is going to have a point on the graph. So the domain's all real numbers. We know the range of this exponential function. So remember the graph of this function here, here's a horizontal asymptote, which happens to be the x-axis. So this is where we're going to start in terms of range right here. We're looking at this right here. So the range is this y value, which my graph never gets to, all the way to infinity. Now, since my exponential function here never touches or crosses the horizontal asymptote, I'm going to have to use a parentheses. So it'll be parentheses 0 to infinity. All right, now let's look at the logarithm. So I'm going to look at g of x, which is log base 2 of x. Now, whenever you write this notation, you have to make sure that your base looks like a subscript. Okay, see, that's a subscript. All right, don't put it even with or level with the x here. Okay, the base has to be written as a subscript, so make sure it looks like that. All right, so those are inverses. The base here is 2, the base here is 2. All right, now let's look at the properties of this log function. So notice that the log function has a vertical asymptote. So as I go to the left, my y values are getting close. I'm sorry, my x values or my points rather, my graph is getting closer and closer and closer to the y-axis, right? So you're getting closer and closer and closer to the y-axis. So it never crosses the y-axis. Okay, it does not cross the y-axis or touch the y-axis in this case, because the y-axis happens to be the vertical asymptote. So instead of having a horizontal asymptote like the exponential did, the logarithm has a vertical asymptote. So remember, everything is interchanged. So horizontal becomes vertical asymptote. So vertical asymptote. Now remember, the vertical asymptote is a line, right? So that's a line. So let's go ahead and name this line a vertical line. So we name a vertical line, say an x equal. And x equal, in this case, the y-axis happens to be x equals 0. So x equals 0. So notice for an exponential, the horizontal, in this case here, the horizontal asymptote was y equals 0. We interchange. Remember, everything's interchanged. Y equals x. So y becomes x on the logarithm. So x equals 0, which happens to be the vertical asymptote. Horizontal becomes vertical. Let's get the domain, though. All right, so I want you to think about the domain and range. First of all, let's look at the range. So remember, range is where we go from bottom up. Now I'm looking at the range of this logarithm here, this graph, this function. So when I look at the range, remember this keeps going down, right? So I'm going from negative infinity all the way, and see I keep on going up because this graph keeps rising, doesn't it? Keeps going this way, all the way to infinity. So my range is negative infinity to infinity. My domain, remember the domain is a set of x coordinates. So notice that for this logarithm, I start touching the graph when I go from left to right. I kind of start touching the graph when I get to the y-axis, although I don't touch the graph because it never touches the y-axis, but it goes from 0 all the way to infinity. I have to use parentheses because this graph never touches the y-axis. So this is going to be, so the domain will be 0 to infinity. What I want you to notice is this. The domain of an exponential is the same as the range. Remember, everything's interchange, right? When you talk about inverses. Horizontal becomes vertical. Y equals 0 becomes x equals 0. Domain becomes the range. Range becomes the domain. So everything is interchanged when you talk about inverses. All right? So the domain of a function becomes the range on its inverse. The range of a function becomes the domain of its inverse, on its inverse. All right, so horizontal exponential function has a horizontal asymptote. Logarithmic function has a vertical asymptote. A horizontal line, remember, is y equals. A vertical line is x equals. All right, now a couple other things that I want to mention, and that's this. If I look at the y-intercept for my exponential, so an exponential function is always going to have a y-intercept because the domain's all real numbers. In this case, though, the y-intercept is 0, 1. Okay, so the y-intercept is 0, 1, and you can see that. That's where the graph crosses the y-axis. There's no x-intercept because the x-axis is the horizontal asymptote. The graph never touches or crosses the horizontal asymptote. But I want you to notice something. 1, 0 becomes, see this y-intercept? Look at the x-intercept here of the logarithm. That's why the graph crosses the x-axis. So the y-intercept, 0, 1, right, of an exponential becomes the X-intercept on its inverse, although we have to write the ordered pair differently. So it crosses that 1 here, or cross that 1 here, although when saying the X-intercept, we have to put 1, 0 instead. All right, so the y-intercept here is 1, on its inverse becomes the X-intercept. But the ordered pairs are different. You obviously see that. So 0, 1, 1, 0. All right, so y-intercept becomes X-intercept. All right. Let's see. Okay, so couple of things before we look at another problem is this. So remember the inverse of an exponential is a logarithm. Okay, the base here becomes the base here for the logarithm. You know that an exponential and a logarithm are both symmetrical about the line y equals x because they are inverses of each other. So they are symmetrical about the line y equals x. And you also know now that an exponential function has a horizontal asymptote, a logarithmic function has a vertical asymptote. You also know that the domain of an exponential becomes the range of its inverse, which is a logarithm. You also know that the range of an exponential becomes the domain of its inverse. You also know that the y-intercept, an exponential function always have a y-intercept, okay? And you also know that a logarithm always has an x-intercept. It's always going to cross the x-axis because the range is all real numbers, so it has to have an x-intercept. But you also know that wherever the graph crosses the y-axis on the exponential, it's going to cross the x-axis on its inverse, on the logarithm. Okay? All right, now let's look at another example. Let's look at this example. All right, so let's graph the inverse of this exponential where the base is e. Now remember, e is an irrational number, so remember that in your calculator has an e function on your on your calculator. So it's right above. You can't, let me see if I can move it up a little. See right above here, right above the ln, right here, e to the x. So that's how you get to it. All right, now, so to graph this, let's go ahead and plot some points. So if x is 0, that's always the easiest to use. So remember, the domain of an exponential, let me just remind you, the domain of all exponentials, of all exponential functions, is all real numbers. Negative infinity to infinity, all real numbers. So I can use any number for x. So 0 is in here. So always use 0 when dealing with an exponential. So if x is 0, I get e to the 0, which we know is 1. Okay? If x is 1, I get e to the first power. Now let's go ahead and approximate this. So let's remind ourselves how to find e to the first power. So e to the first, so to get to the function e, I've got to press second ln. See that? And then I get e. And I want to raise to the first power, like this, close the parentheses, and then we get this. Now remember, this is actually e. E is an irrational number that's approximately equal to 2.718, and we usually round off to the thousandths place. So 2.718. So e is approximately equal to 2.718. Okay. So let me put 2.718. If x is 2, I get e squared, and let's approximate that. So I'm going to say second ln rather, to get the e function, and then 2. So e squared is approximately equal to 7 to the thousandths place, 7.389. So 7.389. All right, and since I'm using this coordinate grid right here, since I'm using this, I know that the highest y value is 11 here. So if I go 3, it's going to be much bigger than that. So let's use a negative number. E to the negative 1 is approximately equal to. And so second ln, negative 1, close the parentheses, equal. So that's about 0.368, right? 0.368. 0.368. 0.368. All right, now remember, this right here I can rewrite as f of x equal e to the x plus 0. So that means that my horizontal asymptote is, remember, an exponential always has a horizontal asymptote. The horizontal asymptote is y equals 0, which happens to be the x-axis. All right, so let's go ahead and graph what we have and see what we get. So e to the, so 0, 1 is here. I know that the x-axis is my horizontal asymptote. I know that. I have 1, 2.718, so that's about here, let's say. Okay, right here. And then I have 2, 7.389, 2, 7.389, let's say it's about here. All right. And then 1, negative 1.3, let's say, is around here. Okay, so that's about all I'm going to graph. I do know, remember, your graph gets closer and closer and closer to the horizontal asymptote without crossing it. Again, don't make it look like it goes back up, because we talked about that before. Some students inadvertently make the graph look like it's going back up, and it doesn't. It gets closer and closer to this horizontal asymptote. On this side, though, as you go from left to right, the y values rise very rapidly. So the y values get larger exponentially. All right, so there's the graph of f of x equal e to the x. All right, now I want to graph its inverse. Okay, so let's graph its inverse. So to graph its inverse, I'm going to reflect this about the line y equals x, because remember, inverse functions are symmetrical about the line y equals x. So 1, 1, 2, 2, 0, 0, negative 1, negative 1, negative 2, negative 2. And I'm going to denote that by using a dotted line for the line y equals x. So here's y equals x right here. And so there's y equals x. All right, so we're going to reflect this about this line. So we're going to graph its inverse. So you see this point here. Remember, all exponentials have a y-intercept because the domain is all real numbers. So since the domain is all real numbers, there's got to be a y-intercept. Well, the y-intercept, remember, becomes the x-intercept. So 0, 1 becomes 1, 0, right? This point here, which is, and let me go ahead and find it here. So you see this point here? That is the point 2.718. So that becomes the point 2.718, right? So that's about here. Okay? And then this point here, which is 2, 7.389, 7.389 becomes the point 7.3892. So everything is reversed, interchange. So I said 7.389, 7.389, which is about here, and then 2, right? So that's about here, let's say. And remember, the horizontal asymptote becomes the vertical asymptote for the exponential. Remember that? All right, so then we get something that looks like this. And remember, it gets closer and closer and closer to the horizontal, to the vertical asymptote, and then you get something that looks like this. Okay, so this graph and this graph are inverses of each other. You can see that they're symmetrical about the line y equals x. All right, now let me remind you how to write the function here for the inverse of an exponential. So remember, we talked about the logarithm, right? So the inverse of an exponential is a logarithm. Okay, I'm going to write this first, but then we're going to change it. So I want you to write this. You're going to say y equals log, L-O-G, and this base has to equal this base. So this base is e, then this base is e. Make sure you write as a subscript. It's got to look like a subscript. And then x. Now, the next thing I got to remind you is this, and you learned this in a previous lesson. Whenever the base is e, then really that means this notation. So it'll be called the natural logarithm. A logarithm with base e is called a natural logarithm. So we just say natural log of x. So the inverse of this exponential, which has base e, is the natural logarithm. So ln of x. So you have to remember that when you see the function ln of x, that's the natural logarithm. Let me write it down. The natural logarithm, called the natural logarithm. All right, so the logarithm, the natural logarithm, has base e. So it's understood to have base e. So both of those are equivalent, but this is the way you have to write it. You have to write it with ln. You got to keep the mathematical notation consistent. Okay? All right, so that is the inverse of the exponential function with base c. So the inverse of an exponential function with base c is the natural logarithm. And that has, remember, base e. Okay, so a couple other things I want to remind you, just like we did in the previous problem. So if you compare the exponential function with base e with the natural log function. If we compare the two, let's look at that. So f of x equal e to the x, and then g of x equals the natural log of x. Okay, so remember the all exponentials, the domain's all real numbers, right? Domain's all real numbers. So the domain of an exponential, which is all real numbers, becomes the, got to remember, so the domain becomes the range, right? So the range would be all real numbers. And it kind of makes sense because if you look at this, look at the logarithm. So we look at the logarithm as you go from bottom up along the y-axis because we're looking at the range. See this arrow keeps going down, right? So you're going from negative infinity all the way to, and just keep going up. See, it keeps on going right here, right? All the way to infinity. So the domain becomes the range. So the domain of an exponential becomes the range of its inverse, which is a logarithm. When we talk about the range of an exponential, so remember the range of this exponential that we're looking at here is from, remember you start at the horizontal asymptote, which crosses at y equals 0. So go from 0 all the way to infinity. You cannot include 0 because remember the horizontal, the graph never touches the horizontal asymptote or crosses it. So we have to use parentheses. So parentheses 0 to infinity. Well, the range of an exponential becomes the domain of its logarithm, of its inverse. So the domain of its inverse will be 0 to infinity. And if you look at it, it kind of makes sense, doesn't it? Because here's the logarithm, the inverse of this. And as you go from left to right, notice when you start looking at the graph, at that vertical asymptote. So the vertical asymptote crosses the x-axis at 0. So you're going from 0 all the way to infinity. All right, and that's what you see here. The exponential function always has an x-intercept. Whatever the x-intercept here is going to, an exponential function always has a y-intercept, a y-intercept. That's where the graph crosses the y-axis. But wherever the graph crosses the y-axis for the exponential, that's where the logarithm, its inverse, is going to cross the x-axis. See, crosses it 1 here, crosses it 1 here. Okay? So the x-intercept, so an exponential function always has an x-intercept. In this case, it is 0, 1. On its inverse, it's going to cross that same point at the y-intercept. Y-intercept here. I apologize. So the exponential function has a y-intercept, always has a y-intercept. For our logarithm, it's going to cross at the x-intercept. So the x-intercept, which will be 1, 0. Make sure you write the coordinates correct, though. So the point's the same, the number's the same, y-intercept 1, x-intercept 1. Just remember, though, when you write the coordinates, you got to be careful with the x and the y's. And let's see, I think that is, oh, and also remember that an exponential function has a horizontal asymptote, right? A logarithm has a vertical asymptote. So the horizontal asymptote here is y equals 0. Then how are you going to write the vertical asymptote? So the vertical asymptote will be x equals 0. Kind of makes sense because look, here's the horizontal asymptote for the exponential. Here's the vertical asymptote for the logarithm, for its inverse. All right, so the inverse of the exponential function e to the x is the natural logarithm, ln of x. All right, and then finally we're going to look at an exponential function where the base is 10. Now remember, when the base is 10, this is called a common base. So that's called the common base, C-O-M-M-O-N. So this common base. When the base was e, that was called the natural base. So natural base. And so that's why we call it a natural logarithm. Natural base, natural logarithm. Okay, so if the base is 10, let's go ahead and plus some points, just like we did before. If x is 0, and remember the domain's all real numbers because it's an exponential, so all exponential function, the domain is always going to be all real numbers. So I'm going to use 0. And if x is 0, I get 10 to the 0, which is 1. If x is 1, I get 10 to the first, which is 10, right? Now at this point, it gets very large, and I don't have room in my plane to graph any other points bigger than x equal 1. So for example, if x is 2, I get 10 squared, which is 100. So you know there's no way I can plot the point 2, 100 in this particular plane here because it goes up to y equals 11. If x is negative 1, I get 10 to the negative 1, which is 1 over 10, which is 0.1, right? And negative 2, I get 10 to negative second power, which is 1 over 10 squared, which is 1 over 100, which is 0.01. I'm sorry, 0.01. Okay. All right, so when I plot those points, though, I want you to see something, see what the graph looks like. You have the Y-intercept at 1, right here. You have 110, which is up here, and I can't go any further. So it rises very rapidly. And then you have negative 1.1, which is very close to this horizontal asymptote right here. And so you get something that looks like this. And it rises extremely rapidly. So it kind of looks like this compared to the others that we've drawn. Rises very rapidly. Looks like that. Okay? All right, now I want to graph its inverse. Remember, this is f of x equal 10 to the x. So I want to graph the inverse. We're gonna graph this about the line y equals x. So 1, 1, 2, 2, 0, 0, negative 1, negative 1. And let's go ahead and graph this line using a dotted line. So we get something that looks like this. All right, so y equals x. All right, that's y equals x. All right, so the point, so remember this is your y-intercept, right? The y-intercept, the exponential. So the y-intercept and exponential becomes the x-intercept on its inverse, which happens to be, remember, the logarithm. So 1, 0. This point here, which is 110, becomes 10, 1. So about here, right? And then the horizontal asymptote becomes the vertical asymptote, like this. Becomes a vertical asymptote. And you see this point right here? That was a point negative 1.1, so it becomes 0.1, negative 1, about right here. So you get something that looks like this. Now remember, when you draw it, don't make it look like it touches or crosses the vertical asymptote. And you get something, oops. Let's see, that's about here. So you get something that looks like this, right? It looks pretty flat, but it's not. So I tried to, and it doesn't look very well. Oops, I did mess this up. That's 10, 1, excuse me. 10, 1's here. Apologize. 110 becomes 10, 1. So let me go ahead and take this part away right here very quickly. You see what I'm doing? So I put the point in the wrong place. 10, 1's right here. So let me kind of take this off. All right, so you get this now. You get, all right, all right, so you're going to get this. Let's redo this like this. All right, so now it looks a little bit better. So that graph and this graph are inverse of each other. They're symmetrical about this line, all right? And I want you to notice, so remember when we wrote this, I want you to write it like this for right now. I'm going to tell you how to rewrite this. So what you notice is that this base is 10, the common base, right? So when you rewrite, you're going to say the log base 10 of x. But what I want you to remember, and you learned this in a previous lesson, is that a logarithm that has base 10, we tend not to write the base 10. We prefer to use this notation, just log of x. So if there's no base here, it's understood to be base 10. So this is what we want you to write. So don't write base 10. Write what in mathematics we write it as. We write it as log of x. And this is called the common logarithm. So common logarithm because the base is 10. So that's common logarithm. Okay? All right. So we did 3 examples where we graphed the inverse of an exponential, and we saw that the inverse of an exponential is a logarithm. The base of the exponential is the same as the base of the logarithm. And we saw several things. We saw that the horizontal asymptote of an exponential becomes the vertical asymptote of the of the logarithm. We saw that the domain becomes the range becomes the domain, and all that, right? Okay, so let's finish this up. So we already know the domain for the exponential is all real numbers, because remember, all exponentials, the domain's all real numbers. So let's go and compare those two very quickly. So f of x equals 10 to the x, and then g of x equals the log of x. Remember, the log of x is understood to be base 10. So that's how we write the common logarithm. So when you see this, where there's no base listed, that's called the common logarithm, common log. All right, so we know that the horizontal asymptote of an exponential for this one here is going to be y equals 0. So we know that an exponential has a horizontal asymptote, a logarithm has a vertical asymptote, and it's going to be x equal, in this case, 0. We also know that the domain of this exponential is all real numbers, and so the domain of an exponential becomes the range of its logarithm. So the range will be all real numbers. We know that for this particular function, when we look at it, the range for the exponential, the range goes from 0 all the way to infinity. Parentheses 0 because the graph never touches the horizontal asymptote. So the range will be 0 to infinity. The range of an exponential becomes the domain of the logarithm. So the domain has to also be 0 to infinity, and it is. Because look, when I look at the logarithm, when I look at this logarithm, notice this is a graph, right? So when I go from left to right, because I'm talking about the domain, I go from 0 all the way to infinity. So it keeps on going, all the way to infinity. And that's what you see here. We know that an exponential function always has a y-intercept. In this case, my y-intercept is 1. I'm going to write as an ordered pair. It's 0, 1. It becomes the x-intercept on the logarithm, on its inverse. So the inverse, the x-intercept will also be 1, but we got to write as an ordered pair, so we're going to say 1, 0. Okay, so remember, 0, 1 becomes 1, 0. Okay, the coordinates are interchanged. All right, so that is this lesson, and on this lesson, I just wanted to show you first of all that the exponential function, its inverse is called a log function, and I wanted to remind you that to graph the log function, you can first of all graph the exponential, and then reflect it about the line y equals x, and that gives you the log function. All right, so that is the lesson on graphs of exponential functions and logarithmic functions.